So important identity theorems. Theorem 1. If f and g are analytic in a domain D and f is identically equal to g in some open disk contained in D, then f is identically equal to g throughout D. The meaning is D is the domain here. Instead of checking whole domain how the functions f and g are behave, it is enough to check in the open disk itself. For the values in the open disk, the functions are equal, then the functions are equal throughout D. Okay. In the second theorem, instead of some open disk, here we are taking infinite sequence of distinct points. So instead of open disk, for all the points in the open disk, we are taking infinite sequence of distinct points. Okay. So for these points, the functions f of zn equal to g of zn are equal. Then, and one more important condition is the sequence of distinct points must converge to a point z0. That z0 must be in D. This point is very important. z0 must be in D. Then the two functions are identically equal throughout D. Throughout D means for all the points in D. See the question. This type also very important, repeatedly asked. Let D is the set of all z such that modulus of z less than 1. This is called unit disk. Let f from D to C. C means here set of complex numbers. Be an analytic function satisfying f of 1 by n equal to 2n by 3n plus 1 for n greater than or equal to 1. Then, so what about these options? So we are here we are using the identity theorems. Here check 1 by n tends to 0. That 0 is in D, that is open disk. And f of 1 by n equal to, this is given. Take this n outside. This n can be cancelled. Okay, this n can be cancelled. So the remaining values are given 2 by 3 plus 1 by n. Now consider the function g of z equal to 2 by 3 plus z. F of 1 by n equal to g of 1 by n for each point in the sequence. Take any sequence 1 by n. This means put n equal to 1 means both the values will be same, like that. Hence we get f is identically equal to g. So instead of checking f, now we can check using the function g. So what is the first condition? F of 0 equal to 2 by 3. Find out g of 0. G of 0 equal to 2 by 3. So first option is correct. And then second one, f has a simple pole at z equal to minus 3. Pole means I will say later. Put the denominator equal to 0. 3 plus z equal to 0 means z equal to minus 3. So it is a simple pole. That's also correct. And then third option, put f of 3 equal to 1 by 3. So g of 3 equal to 2 by 3 plus 3, that is equal to 2 by 6. So that is equal to 1 by 3. So this option is also correct. The final option, they say no such f exists. They exist. That's then only you can find out all these values. So this option is incorrect. Only options A, B, C are correct. Let C from C to be a meromorphic function analytic at 0. Meromorphic function analytic at 0 satisfying f of 1 by n equal to n by 2n plus 1 for n greater than or equal to 1. Meromorphic function means it is analytic except up to finite number of poles. Okay, meromorphic function is an analytic function except at finite number of poles. Then, so what are the options are correct? Same model. Here 0 is a accumulation point because 1 by n only we are checking. 1 by n tends to 0. That 0 is in the whole complex number. Here domain is the whole complex number, so no problem. And then f of 1 by n can be written as take n outside and then divide by cancel by n. So we get 1 by 2 plus 1 by n. Take the function g of z equal to 1 by 2 plus z. These both satisfy. So f equal to g. F equal to g. So clearly we can check by direct substitution like the previous problem. The options A, B, C are correct. Only option D is not true. No such meromorphic function exists. Hence the options A, B and C are correct.